Hi, my name is Dan Gilliland. This is Lab 2, Magnetic Field of a Bar Magnet. I just want to point out that in this experiment we are going to have to make the assumption that our equation for the magnetic field due to a dipole models the magnet's actual magnetic field well, because far away from the magnet it does. Bit of an introduction to our experiment here. The purpose of this lab was to measure the distance dependence of the magnetic field due to a bar magnet using Biot-Savart law and distance dependence equations for magnetic field, and represent that magnetic field visually using VPython. A few of the fundamental principles we'll be using here. The first one I'll circle in red. That is our Biot-Savart law for the magnetic field of a dipole at any location. And then the next ones above it, I'll circle in blue, are the equations that we will use to determine the magnitude of the magnetic field due to a dipole. And what I'll circle in green here is an equation that we are going to use to linearize our data that we are going to collect during this experiment. Our system in this experiment, you could say, would be the magnetic field from our magnet. And our magnetometer and the space between. Now, some of the surroundings you could say would be, let's say a computer I have nearby creating an electromagnetic field distorting our results, or gravity due to Earth. So those are some of the surroundings that will have an effect on our system. Brief preview of some of the results. I found that the distance dependence value n was equal to negative 2.6209, and our magnetic dipole moment mu was equal to 4.428 Newton meters per Tesla. Here's the data I collected during the experiment. On the top left, over here, we have our on-axis magnetic field, and over here we have our off-axis magnetic field data. The graph is from the on-axis magnetic field, and we have the natural log of Bx versus the natural log of R, which is where we got our n value right here, which is the slope of this graph, which is that negative 2.6209. Here's where I calculated the magnetic dipole moment mu. Took the equation from the graph of our data, and we're going to plug it into this equation here. Remember, our n value is this, and for our R value, we're going to use 1 meter. Well, ln of 1 is 0, so we can just take this right out of the equation, and then all we have left is this y-intercept, which is negative 13.937. Now, that is equal to ln of bx, but that's also equal to ln of k. So we want k so that we can start using this equation. So we solve for k, and we get our value here, and then we remember that R is going to be equal to 1, so it doesn't really matter what the n value is, because we can take that out, and then solve the rest of the way for mu, and we end up getting that mu is equal to 4.428 Newton meters per Tesla. On the left, we have the code that I used to create this wonderful visual representation on the right of our experiment and come up with all of these calculations. Now, notice that the orange arrows are twice as big as the blue arrows. That's because the orange arrows are the magnetic field due to a dipole on its axis, and the blue arrows are the same thing except for they are off axes, same distance. Now, this purple arrow up here is the magnetic field 45 degrees from the axes, and our measured value for the magnitude of that we got from our data is 2.28 times 10 to the negative 5, while the computational model is 3.7 times 10 to the negative 5. Now, while those values aren't exact, they are similar enough to show us that our experiment was done correctly. There's definitely areas we can improve, but our data is pretty close. Now, to answer some of the what-if questions, what if we hadn't compensated for magnetic north at the beginning of our experiment? Well, our results would have ended up being from the superposition of the Earth's magnetic field and the magnetic field from our magnet. Also, what if we imagine that we had two identical magnets and we stuck them together and redid it? Well, I would expect the results to be similar, but just multiplied by some positive scalar value. It would be similar to if we just did the same experiment over again with a different strength of magnet, most likely stronger.